Oh, okay. We can't. No. What's that? Oh. There we go. Okay, that's good. All right. Today is going to be somewhat short because I have a meeting off campus this afternoon, so we're going to be leaving shortly after 1:30. Oh, you're going to try to move it over a little bit, huh? Yeah, there you go. As long as it'll stop bouncing eventually. That there. All right. Today is going to be, as I was getting ready to say, it's going to be relatively short because I've got a meeting off campus this afternoon that we're all having to head out for, and we have to leave by right after prayer. So that there. Although I normally talk an hour and 15 minutes, so it'll be probably a little bit shorter than normal. I put up on Facebook this morning a lab experiment that we're going to be doing over the next week or so, and let me just kind of talk about this lab. I've done it before, but there. And the lab assignment is basically, eventually we're going to do something with Watchdog Timer, but that's going to be for our next lab. This lab here is we're just going to go through and we're going to learn how to add and multiply with this processor. And you're going to find it's a pain in the neck. So I didn't bring a board with me, so I'm not going to demonstrate this. Actually, you'll be doing it in the lab on that there. There's 3 parts of the lab that there. Ignore this right here because this here, use Blinky as your shell. That there. Use Blinky as the shell. Just open up Blinky and then save it as Lab 2A, Lab 2B, and Lab 2C. So there's 3 parts of this lab that there. So I'm planning on you spending 2 weeks on this lab right there. And I'll be honest, I've asked people on the final exam to write parts of this lab. So it's not only do you need to do the lab, you also need to understand how the lab works because it will find itself on the final exam as well, where I'll ask you how to do certain things up there. So part A, right there. Part A is relatively simple. Is write a program that type program Silicon Labs IDE and try it out. Use the following code to start with. Actually, this code is okay. You can start with this code here. That's perfectly fine. That there. So, right there, it's got all the key parts to it. But remember, you've got to put the long jump into main at the beginning. So you need to actually put that first part in there where you. From Blinky, let me pull up Blinky here. Desktop. Blinky.asm. And open with. And I'm just going to open it up with WordPad right there. Now, Blinky, this is wrong here. Actually, our file name, I just called it blinky.asm. It's that there. And our target MCU should actually be 850 right there. So I took this lab from another lab. So, but we include the 8051 F850. Here we had a couple of LEDs. We're not going to use those this time, so you can actually comment those out right there. Those 2 lines can be commented out right there. That there. You need to have this line where you set the CSEG at 0 and long jump to main. That's not in the lab description, but you need to add those lines there. Blink, just call it multiply 8 or whatever you want to call it there. RSEG blank using 0 right there. Everything up to here you need to copy from Blinky right there. Everything up to there needs to be copied right there. And whenever I try to copy that and put it on Facebook, and I don't have Facebook in this room anyway, it seems to give me trouble. So just remember that everything up to enable the crossbar, you have to copy. Now you don't have to use any of the I/O this time. So you don't need to worry about enabling the crossbar or setting up the ports right there. So you can skip all this part right here. All this can be skipped right there. The simple delay loop, that's all for Blinky. So all this here, everything here, just ignore that, just delete it. So use the shell just as it is there. And let me just delete that and file save as, and I'm going to call it shell.asm right there. And I'll post that probably tomorrow because I won't have time this afternoon to post that there. So your code actually, and I'm going to put a comment right here, repost, resave it. Your code starts here, right there. So this is where your code will start right there. Right there. So, and I'll put a semicolon there and a bunch of dashes across that there. So this is where your code will actually fit right there, is between those two lines. Your code. So you would actually put your code right there. So first off, let's look at part A, and I'm going to kind of describe what needs to happen here, right there. And you'll have to go back and look up, and I'm going to bring up PowerPoint. I don't want reader. I want desktop, and I want and I'm going to bring up the instruction set because you'll need to look at the instruction set to write your code right there. So as we look at our instruction set, here, I'm going to jump down here. We don't need any of this stuff for the instruction set. We're going to go through all the various addressing modes right there. Long addressing, and I'm going to jump down here to the arithmetic operations because that's really where we need to look at for our instructions right there. In particular, multiply A and B right there. So the first part of the lab is very simple right there, and I'm only going to talk about the instructions we need to do. And so the first part of the lab is we just multiply performs a simple 8-bit multiplication right there. Store the answers in registers R0 and R1. R0 contains the high order byte. R1 will contain the low order byte. This doesn't tell us where to put our two numbers we want to add. I'm just going to say, for sake of argument, that I'm going to put them in registers 2 and 3, high order byte and register. Well, actually, they're just in 2 and 3 because it's 8-bit numbers right there. So the way you would typically do this there, and I'm going to basically go through that there is when you do the lab, don't run the lab. Just single step through it and look at the registers. And I'll go through that on Friday and Monday on how you would do that in class during the lab. But your code is going to look something fairly straightforward right there. So we say that R2 and R3 contain the numbers we want to multiply. So these contain the two numbers. Numbers to multiply. And now when we multiply two 8-bit numbers, we get a 16-bit answer right there. We're going to get a 16-bit answer is what we're going to get that there. So if we go back and we look at our multiply command, right there. Our multiply command is multiply A and B, that there. And if we go through and we look at, let's just from current slide, we look at the multiply command right there. It multiplies A and B, and the result is stored in B and A at the end of the multiplication. The high order byte is in B, the low order byte is in A, right there. This multiplies 2 in the accumulator and the B register. So the multiply command only can operate on A and B. You cannot use any other registers for that. That's a restriction of the instruction set of the 8051. That there. So when we multiply the two numbers there, we're going to get the result here. This gives an example of 55 times 23. It's going to give us the answer as 07A3 right there. So, and if I bring up my calculator and I go back to programmer mode and I go in hex, and what was our two numbers that this gave? 55, 23, right? So I take 55 times A3, the result is, all right, 36. Oh no, that wasn't right. Oh, 23. The A3 is the answer. So 55 times 23, our answer is B9F. That doesn't agree with what this is saying right here. Maybe, this is giving me, 55 hex times 17 hex. All right, I need to be working in hex in order for this to work. Right there, I didn't read the slide properly. Right there, so it's 55 hex times 17 hex. Right there. So it's saying 85, it's 55. So ignore the 85 and 23 and just work in hex. So it's 55 times 17 equals 07A3. That gives me the right answer right there. So as long as I read the slide properly and I get the same answer as the slide. Right there. You can pick any two numbers you want. I can take 45 times 63, and these are hex numbers. I'm going to get 1A and AF right there. So that's how you would test to see whether you've got the right answer. So the way we do this is fairly simple, is we just simply move, and then you got to remember that we got to load R2 and R3 first. So move into R2, number 55, move into R3, number 17, right there. And put an H at the end of that right there. Right there. So that preloads it. So this is just preloading this before we do our multiplication right there. So then all we do is we just do a move into A, R2, move into B, R3, right there. And then we do multiply AB, right there. We just multiply the two. Now we want to store B, move to register R1. Oh no, it's R0 is they want to be the high order byte, right? So B and move into R1A. And you're done. That's the whole first part of the lab right there. It's fairly straightforward. So that's the code you would use for the first part of the lab. And then you could do a jump back to main if you want to do it again right there. So again, all you're doing is every time you single step through this, you want to see the data move from R2 to A. You want to see the data move from R3 to B. You want to multiply, see what A and B are, and then do your move right there. So this is the easy part of the lab. I basically told you how that's done. The second part of the lab is to add two 16-bit numbers right there. Now, we could do equates actually if we want to make it a little bit easier right here. And this is the way that we do the equates. That way we don't bother with putting it in the registers first right there. And store the answer in high byte to lowest byte that there. You could possibly have 3 bytes of data right there. So when you do that there. So we've got 3 numbers we want to add. Num 10 20. This is the first number right there. It's 16 bits wide right there. The second number is 16 bits wide. We've got an 8-bit processor, so we can only add 8 bits at a time. So, but when we do the addition, we may have a carry out right there. So we have to keep in mind that we may have a carry out. So when we do the carry out, we can have up to a 17-bit answer right there. That's what we have right there. So if you're reusing your code from above, remember our 8-bit numbers, replace them with the following right there. You could also do that with, they didn't show that there, but you could, instead of doing the move from, going back to my, right there, you could also, instead of doing this, you could do the equates there and skip those 2 steps and just do the equates right there for that there. So going back to this discussion here, we have 4 numbers right here. We have num 10, num 11. Is that what I called them right there? Right there, num 11 and 10. 11 and 10. So they're 11 and 10 right there. And that's the equate. And I'll just put 23 hex and equate 15 hex right there. So I would sit there, and then we have num 21 equate 17 hex and num 22 equate, and I'm going to say F0 hex right there, and you got to put a 0 in front of that there. So, and right there. Oh, actually, I'm using the H here. You got to put the 0x in front. So I'm giving you the wrong format there. So these H's disappear, and this becomes 0x, 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 and 0x right there. And anytime you have a number that starts with a letter, you got to put a 0 in front of it right there. So those are our 4 numbers right there. So we're just going to add those together. So we're just going to move to a num 10. You got to do it in that fashion right there. And I got to put the number sign in front of that so that it knows it's immediate data and not an address right there. And then we do an add a right there num 20 right there. So we're adding the 2 lower 8 bits together. That's what we're doing right there. So now we want to move that to our registers right there. And as we look at our registers, our low order byte, our low order byte goes into R2 right there. So this is our lowest order byte. So we move to R2A right there. So that stores the result. Now if we have a carry out, it's going to save that carry out in the carry flag. So the next time we do an addition, we need to do a add with carry. So now we repeat this process. We move to a number 11. We add with a carry to a number 12 right there, or excuse me, 22 right there. So I'm giving you the hints on the first two parts of this. I'm actually writing it for you, although you're going to type them in and test through that there. Now we move this to R1A. So we store the result. We're not done yet though. Now we come to the tricky part. What happens if we have a carry out of the second one right there? We can do two things. One is we can just go ahead and add 0 to 0, move a 0 to A, and then add 0, do an add with carry, which is probably one way of doing it, or we can do a jump if carry. So I'm going to show both ways. One way, and this is probably the more difficult way, but is we move to a 0 right there, and we do an add with carry a 0 right there. Now what do these two lines do right there? We're adding 0 plus 0, right? Our answer should be 0. But if there was a carry from the second addition, that carry will be added in. Whenever you do an add a number, we'll say 23, A is going to be equal to A plus 23 plus C. C is either a 0 or a 1. It's the carry flag or it's a 0. So if the carry flag is a 0, it's a 0. If it's a 1, it's a 1. So when I add 0 to 0 with a carry, if there was a carry after this addition, that 1 will now be an A. So then I would move to R0 right there. So that would be our 16-bit add right there. That would be our 16-bit add right there. So there's the first two parts of the lab. That's what I expect you to get finished tomorrow. And again, you need to single step through this and see as everything's going through this, as things are moving, and understand how this code works. The other way of doing this right here is I can do a jump if carry. Actually, it's easier to do a jump no carry right there to no carry. That's just a label that I'm going to put in there. If there is no carry, it's going to do a jump. Move to R0 a 0 right there. Right there. Or excuse me, a 1 right there. And then do a jump back to main right there. Otherwise, we have our no carry label right there. And here we do a move to R0 0 and then jump to main right there. Right there. So we could do it either way. We can either do a jump if there's no carry, and if there is a carry, then we're going to go ahead and move a 1 to R0, then we're going to jump back to the main. If there is a carry, if there is no carry, then we're going to move a 0 to R0 and jump back to main right there. So you can do it either way right there. But that's how you would do the second part. That's how you do a 16-bit add. So tomorrow or Friday, I expect everyone to get this part done. The third part of the lab right there, is much more difficult. Because there we're doing a multiply, right there, of two 16-bit numbers. And when we multiply two 16-bit numbers, it involves 4 multiplications and about 8 adds. It's very difficult to multiply two 4-bit numbers right there. But we go through the steps. I'm not going to write the code today because I don't expect you to get through both the third part. Next week you'll do the next part. So probably next week I'll probably sit down and go through how the code would work. But I'm going to explain the third part of this lab today briefly. Right there. So as we look at the next part of this lab, right there, exercise B, right there, store the answers in highest byte in the registers R0 and R2. One of the methods that they're using, there's an example of how you would do that. All right, now we're going to add two numbers together, right there, and this is the carry right there. I kind of went through the solution of how you would do that, right there. So if I took these two numbers and added them together, right there, there's my calculator right here, and I'm going to add 78, I'm going to add, first off, let's set this as a word right there. Actually, I'm going to set it as a quad double word right there because I want to show the carry. If I'm going to add 59 A7 plus FD 78 right there. I add those two together, and that's did I hit add there or did I hit multiply? Let's start this again. 59 A7 plus FD 78 and FD 78. Okay, let's clear all over again. I'm not using my calculator, right? 59 A7 plus FD 78 equals. All right, that's the answer we should expect to see right there. And notice that we've got a carry out right there. But we have to add the 78 A7 first. That gets stored in one of the registers. That gets stored in R2. We add the 59 and FD with a carry. That gets stored in A1. And then we look to see if there's a carry out from that second addition. And we could do that by adding 0 plus 0, using it with add with carry, or we can use the jump no carry to get around adding the 1 right there. So that's the way we would do the second part there. The third part is much more difficult. That there. The third part involves that there. And in this particular case, we're going to be multiplying two 8-bit numbers times 4 times. We're going to do 4 multiplications right there. So the first multiplication we're going to do is we're going to multiply num 10 and 20 right there. Those get stored. Then we're going to multiply, and before I do that, let's just look at how we would multiply two numbers normally right there. So if I want to multiply two numbers, and I'm talking decimal here, I'm not talking that there. I want to multiply 57 times 25, right? We multiply 5 times 7 is what? 35, right? So we put a 5 here, and we put a 3 here. We multiply, that's our first addition right there. So actually what I can do is I'm not going to put the 3 there, I'm going to put it here. And the reason I'm going to put it here is now I'm going to multiply 5 times 5. That's going to be 25 here. Then I multiply 2 times 7. That's going to give me 14 here. Then I multiply 2 times 5. That gives me a 10 here. If I add up all 4 numbers, I got 5. Here I've got 3, 12. Right here. Here I've got 4, and I've got 14, 25. But notice that I did 4 multiplications. When I multiplied these 2, I got this answer right there. When I multiplied these 2, I got this answer. When I multiplied these 2, I got this answer. And when I multiplied these 2, I get this answer. Right there. And I add those up. Now if I pull up my calculator again, right there, and what was those numbers I multiplied? 5725. I'm going to go back to standard calculator. What was that? 57 and 25, right? Yeah, 57. 57 times 25 equals 1425. And that's what I got right there. I get the right answer. We have to do the same thing. We have to do the same process right there. So we have to multiply 4 times and save the result. Now, it just so happens we've got 8 registers, so we can save the result in the 8 registers right there. And then we can do our additions right there. Now, as we look at right here, this is, again, they're doing the same thing here. They're taking 78 times A7, that's this 4E48 right there. Then they're taking 78 times 59, that's this answer right here. Then we're taking our FD times A7, that's this answer right here. And then we're taking these 2, and that's this answer right here. So we're doing the same thing I just did with that there. Now normally when you multiply 2 numbers, you always write that carry on top and you add that in there. You don't do it as 4, you don't show it as 4 multiplications. But when we do this with a microcontroller or microprocessor, we have to do it as 4 separate multiplications. And then we have to add everything up right there. So highest order, this is going to become R0, R2, R1, R0 right there. Now it's fairly easy, once we do our first multiplication, we can move the 48 straight into R0 right there. Right there. But we do our second multiplication right there. Now, the easiest thing to do, to be honest, is since we only have 8 registers right there, and when we multiply, we have to use the B and the A. So we're going to run out of registers if we store this. So we have to set some memory locations right there. So I would just recommend that you just pick some memory, assign some memory locations. We'll talk about how to do that probably next week. But what we'll do is we'll have some temporary memory locations for these statements right there. So, but there, and we could actually use memory locations 8 through 16 because that's the second bank and we're not using the second bank. So we can use for memory locations. So for memory locations, we can use locations 8 through 16 to store our data right there. But we would have to address them with 8 through 16 right there. So we would that there, and the only way you do that is by just not putting the number sign in front of that. So we have our 4 numbers again: num 10, num 11, num 120, and num 22. Those are all equates, and you can put down whatever you want right there. It doesn't matter for testing purposes right there. So right there. So what I'm going to suggest we do is we put those in there and we do our multiplication, and then we store our results in those locations. And you probably ought to keep track of what locations you're going to use right there. Remember, our pattern is, and I'm just going to copy right there, and I'm going to stick it, I'm just going to stick it here, and I'll have to write under it, right there. Right there, okay. Can you still read that? Yeah, okay. Oh, okay, well, all right, well, I'm just going to go ahead and start writing the code there. So what you want to do is you want to identify these, and the easiest thing to do is probably just start and say that this is location F, location E, location D, location C, B, A. What comes after A is 9 and 8 right there. Those are our memory locations. So it doesn't matter what you pick. I just picked them random right there. Actually, it wasn't random. I picked them in an order right there. So the reason we're doing this, we want to store these numbers as we go along, and then we do our addition later, right there. So we're going to do our 4 multiplications first, and we're just going to store these that there. So our first multiplication is we move into A, num10, right there. Put a number sign in front of that, right? Move into B, num20, right? Multiply AB, and move A, which is going to go into location 0x9, and move B 0x8 right there. So we do that for our first multiplication. Now, as I said, I'm not going to write all the code for you. You repeat that for all 4 multiplications. We know that our next multiplication is going to be, and I'm just going to write them down here, right here. Our next multiplication is going to be, we're going to multiply num20 and num11. That's our next multiplication. So we repeat this process, and we store that one in D and C. Right there. Memory location D and C. Then we're going to multiply num, and I can't write today, num11 and that's num21 and num10 right there. The other 2 high and low. In other words, we're multiplying this way here and then this way here. And we're going to store those in B and A, right? Right there. And then our next numbers, or we're going to multiply, is num22 and num12, and we're going to store those in, and actually I got these 2 reversed, but those 2 don't matter, okay? Out there, if we're going down that order right there, and we're going to store those in F and E right there. Right there. So you got to do 4 multiplications right there. All 4 multiplications look exactly like this The only thing that changes is this, and these two right here. 4 out of the 5 lines changes, but you just change num 11, num 20. Next time it's num 20, or follow this there, 21 and 10 right there. And then you store it in these locations right there. And we just go through and we do all 4 multiplications right there. Once we're done there, to get our final answer, we have to move. We could just move. And where is our answer supposed to be? Our answer is supposed to be in R3 is the lowest bit right there, R3. So we move into R3 location 8. 0x8. We move that one there. That one there we just moved. The next one, which I'm not going to go through today, is we would add these 3 numbers to add up right there. We add those 3 numbers right there. And remember that we do with an add carry. These two we do an add without a carry. This one we add with a carry right there. Right there. We have that one with a carry, that there. And then when we add these two, we add it with a carry. And then add those two, we add with a carry. Then we add a 0 to this one with a carry. So we'll go through those steps. I think I've gone through enough today on what we expect. This I expect you to look at between now and next week's lab, that there, and figure out how you want to do it, that there. But this is the lab, and I've set aside 2 weeks for it. Tomorrow's or Monday's lab, I already wrote for you. You should be in and out of there in 45 minutes to an hour, right there, because I already wrote the code for you, right there. So just keep that in mind, that you have to go back and watch the video and type it in from the video, because I'm not going to give it to you typed up, that there. But I wrote the code for you for the first 2 parts of the lab. The third part of the lab is next week, and I've actually wrote the beginning part of it for you. I'll go through next week and kind of show you how you would finish it up right there. So I said today was going to be relatively short because, like I said, we're supposed to be going there, and actually we've got an appointment with the Board of Engineers Malaysia to try to figure out how to get my U.S. professional engineer's license transferred into a Malaysian license. You know, I've been a registered engineer, professional engineer for the last 20 plus years, and now, you know, but you know, I've got to go through and argue with the BEM and see whether or not they'll recognize my U.S. license, which is considerably more difficult to get than the Malaysian license, but that there. And I've been registered for many, many years, and I've worked many years for industry off and on, so I'm clearly qualified as a professional engineer here, but since it's a U.S. certification, I have to figure out what paperwork they need to translate that. To be honest, I don't really care whether I'm registered in Malaysia or not, but Dr. Kyrell does, because I guess the accreditation board asks if I've got a Malaysian license or not. That there, and legally I can practice as an engineer under reciprocity laws. In other words, my U.S. license is recognized here, but you know, the EAC doesn't necessarily recognize it. So it's one of those things that I need to go argue with that there. So I got my big certificate that I can show them, and I got my license and all that, and I renew it every 2 years. So I'm clearly a registered professional engineer. But for accreditation, the department needs to have 3 professional engineers. And if you count me, we have 3. Dr. Kyrell is a professional engineer, and Farus is a professional engineer. Dr. Noor is not. Dr. Lily's got the same problem. She's an expat. She's not a registered engineer. She's a fresh graduate. Dr. Ibrahim is not a registered engineer. He's a fresh graduate. He's not registered as a professional engineer. Dr. Azura, how do you say her name? Azura, the math instructor, she's not an engineer, so she can't get registered. And I don't, and well, actually, I think Bazilla is in the same boat. She's a fresh graduate, but she's a Malaysian graduate, so she has a clear path she should be following, but not there. But it's a little bit more awkward for Lily and Ibrahim since they're not Malaysians. That they're both PhDs from Malaysian universities in electrical engineering, but whether or not the Board of Engineers will recognize that there. And you got to remember, to be registered as an engineer, it's not just the degree. You also have to have, personal letters of references. You have to have so many years of documented engineering experience. It's the same process both in the U.S. and here. I have all of those, but they're U.S. Letters of reference. Plus, quite honestly, that paperwork is 20 plus years old. I don't have it anymore. So if they want to see the original paperwork, they're going to have to go elsewhere. They're not going to get it. But so I get to go do that this afternoon at there. So, and I think it's someplace in downtown KL near Bank Negara or someplace like that. So we have to drive there for our meeting out there. So this lab should not scare you out there. This lab should not scare you. But remember that last year, not the last final, but last year during my first semester teaching this class, I asked the students the process of multiplying two 16-bit numbers. They did not have to write the code, but you have to tell me the process right there, and I'll explain what I kind of went through the process where you have to do 4 multiplications, and each multiplication went into a column, and then you had to then show what additions had to be made. So as we go through and we do part C, you have to remember there's 4 multiplications. You have to identify what the 4 multiplications are, and you have to show what the additions have to be. Because you will end up with, when you multiply two 16-bit numbers, you end up with a 32-bit answer right there. And that's what this is showing right there. Here's our two 16-bit numbers right here. Here's number 1, number 2. These are both 16 bits. And we end up with an answer that's actually, this is the adding. This is our two 16-bit numbers. And we end up with this 4-bit answer. And notice that this 57 here becomes 58 because that, again, we could go through and we do an add 0 with a carry to A, then we end up with that 58 there. We make sure we move this 57 into A, add 0 to it with a carry, and then move that back to our R0. Because this becomes R0, R1, R2, and R3 is what you should get when you go through this. And again, for the report, what you're going to want to do is you're going to want to show what the registers hold at the end of going through your code. I'll do that in the lab. I'll single step through the code and show you what I expect to have in the report right there. So, that there. So, but that's the next 2 weeks on labs right there. Tomorrow, part A and part B, right there. And you write one report for the whole thing. You don't have to write a report for part A and part B and then another report for part C. Just write one report for all 3 groups. And this report can be done as a group, but it needs to be a formal lab report. That's there. So, So as a group, you can divide up the lab reports. This person can write up lab A, part A. Well, this person can write up part B. This person can write up part C. This person can write the introduction. This person can write the conclusion. You can break it up on how you submit the lab report. That there. Part A, and I'm not saying there's 5 in a group. There's 3 maximum in a group. So you would write, one person would do A, B, and C, and then one person would pick the introduction, next person would do the procedure, and the next person would do the conclusion right there. And then the part A, part B, and part C would just be the screenshots right there with a short little, that there. And of course you would have the code that there. And again, right there. This was the code for part B, as I recall right there, that slide right there. No, this is part A, I think, right there. No, this is part B. Part A. Yeah, where is part A? Right there. I can't find part A. You'll have to go through your notes and find where I did part A right there, because that's at there. So with that said, I'm going to kind of conclude. As I said earlier, I was going to finish early today so that we can hit off 50 minutes. That's much shorter than I normally do. Normally I'm pretty consistent right around an hour and 15 minutes normally, I think, right there. So today I definitely intended to be short because I was told no later than 1:30 we wanted to leave.